Hello, thank you for tuning into this video focusing on SQL methods for data analytics. So, what is SQL, or structured query language? By definition, it is defined as a special purpose declarative programming language, primarily designed to define, manipulate, and retrieve data stored in databases, namely relational databases. Much of the language is course constructs is really standardized by ANSI standards, defined from pretty much an updated yearly basis. But various other database systems have also provided extensions to the core SQL language. And so this will vary by specialized platforms or dialects. This being Oracle, Postgres, MySQL, SQL Server, and the like. Traditionally, SQL is used in software development and IT infrastructure, but slowly it's now emerging into the data analytics and data science space, and that's simply just due to the nature of the work. Now we're moving into a centralized platform, cloud computing, as you know, and a lot of the big data infrastructure aspects, and so data analysts, no doubt, will be connecting to back end systems more on a regular basis. And doing so really can open up a lot of advantages for data analytics now that they integrated really a SQL back end solution. And some of these, and I hope to really illustrate this further in the course of this video. But off the broad brushstrokes, SQL is a readable, maintainable, expressive style that follows the human sentence language semantics, and you'll see clauses such as select, from, join, where, group by, order by, clauses that really is easy to read and follow along in its declarative constructs. SQL also is a very fluid. It can be as a special purpose language. It can be layered in application code such as R, and really transferable across platforms because it is a standardized core that's really used in the industry. You could really run an SQL code in R and run that same one in Python or Perl or PHP or C Sharp and Java, and still other platforms, or even special IDEs dedicated to your database backend or command line tool. So that transferability really enhances a lot of the usability of SQL. In addition, SQL can arguably be more efficient with a set based logical order and query and backed by a query optimizer. There is room to add indexes and a lot other performance enhancing elements to the SQL processing, and with all of that, it scales to big data platforms and repositories, and so altogether, you can really use SQL as a complementary tool to do a lot of the heavy lifting with you, across your data pipeline. Often you hear folks comparing R versus SQL, and that really is a wrong comparison. You should really see it as R and SQL. Really in a lot of data analytics operations. And so to illustrate this a little further, I'll be showcasing several methods that you can do that may come up in a lot of analytical operations. And the example data I'll be using will be out of the Botanic Gardens Conservation International. This is an international organization that really focuses on securing plant biodiversity worldwide. Among many initiatives, they maintain a plant threat assessment tool. Users can go to this portal and by plant, family, genus, and species can really look up the assessments by various special or group of plants across various years, and really annotated with sources of those assessments. And so I did just that. I mined that portal and developed a database, a very large, over 90,000 records of plants and their assessments across time. And I imported into an SQLite database. SQLite is a file level as opposed to a server level relational database management system, and it's open source. And so this is a great tool to really show you the feature-rich aspect of a lot of SQL operations. So once I'm running all this in an R Markdown notebook, and you'll see that I'm running no R code, explicitly except on the making the connection and then the final closing the connection. So once using the RSQL Lite library, part of the DBI family of R database adapters, I make the connection to that file level database, and now I've opened up the connection to run queries on them. One great aspect of SQL at the start is just data organization. And this is a very critical aspect in data analytics. You want your data properly cleaned, formatted, and processed so you can use it for the more sophisticated operations, be it plotting, modeling, statistical testing, and so on. So SQL does this very handily and very well and compactly. You really just have one select statement. You can organize and order your columns very easily, and you can even omit columns you don't need. And you directly call the source. This can be a single table or multiple tables with joins, and then set up your order by, and then we're here specifying the limit for so first 10 rows. So a very simple query like this can be connected to your backend, and you can import into your R environment for further analysis. So I mean, it's again one call in R. This will probably be multiple steps just to render the same result. So you do that very seamlessly and fluidly. However, select can even be extended to do a lot of more sophisticated operations, and again, owing to just a set declarative style. You still are working in the select call, but now you can now set up derived columns with using various functions. SQL comes with ships with an array of string functions. You can do parsing, across character columns. In addition, it has a wide assortment of arithmetic operators, mathematical functions. Some even have statistical functions that you can quickly run, in SQL and pull in. And so, as you can see, doing a very sophisticated, parsing of the plant name, where I'm trying to remove the last part and keep only the first two identifiers for a more cleaner column overall. And so, and then you can even set up logical calls. And this, the corollary in R will probably be the if else. And you can do this nicely and seamlessly again, still in the select statement. So if interpreted conservation status is equal to data deficient, we'll create a missing value, and then otherwise return the non-missing value. Set up a study year compared to the first year 1970, and so on and so forth. And so you can get a nice clean format in a very compact statement without too much wrangling and really too much helper objects flooding your global environment. So we can then even jump into certain aspects of SQL across data objects. SQL is really based in a set based operation. Tables are written, and views and all of its result sets are really seen as sets, and really sets in the mathematical sense of set theory. And so there might be times when you're working with group clusters, samples, representation, and you want to see and compare between sets. And so a lot of the clauses that come with SQL can help in that. And one is a union clause. Let's say we split our data by the not threatened and the threatened statuses of plants, and we'll compare the geographic scope and see how they come out. So with a union, you'll be pulling all values from one and the other, and then returning a deduped list. And so as you can see, over 37 rows of all such values. And so you get a nice pull out of that. Then you can adjust that. You can now look at what are the matching between these two sets, and you can use that with the intersect clause. So you get now a reduced list. Now this is 22 rows of all those corresponding values. And then you can still go further and do an except. What values are in one list, one set, and not in this in the second, the subsequent. And in this one, the order matters. Where the first one is the actual returned values we want, and then the second one is more the comparison. And so we can then see which values are in one and not the other. And so again, this helps with representation, see what's missing, what's not matching in your group analysis or cluster analysis. And then you could do vice versa, switch them, and then now look at what fields are in the not threatened versus the threatened. And this only comes out with 3 values overall. Going further, SQL, again, owing to its set-based design, we can run a lot of pairwise combination permutations across various values, especially with the extension of join. Now we introduce join into the select statement, and what join does is it essentially merges two different sets across various logic. Cross join is just overall, so it returns a Cartesian product. You're not matching by any, so you'll match all rows by all rows. And so sometimes you may need that when you're setting up balanced panel models, longitudinal. You don't want missing, groups in 1 year, or missing years in one group, and so you want a balanced set overall, and then maybe fill in, or impute your data late on a latter step. So we can do just that, return all distinct values, all the major groups of plants, and then all the assessment years, recall from 1970 onward. And major groups here is just 4 distinct values overall. And then we can do a further cleaning. Let's leave out missing values, and then we can order by our groups. The return Cartesian product. And so as you can imagine, that's a very voluminous. We have over 150 rows for that set. So, and then again, join can be its sibling, counterparts. There's the inner join, the left join, the right join, and the full join. And so you can use all of those to really make matches or pairings between different sets, and not just two. You could do more than two. And then aggregation. This is probably one of the premier reasons to use SQL, in that you can aggregate your data in a very compact and efficient manner. Aggregation is a very a known exercise in a lot of data analytical operations. We do this prior to running any modeling, to see distributions, to see how the numbers play out across groups. And so SQL can lend a great hand in this effort. And one reason is because you can easily set up multiple groups and multiple aggregates. And so here we're only using one group, the major group, the 4 major groups of plant species. And then we can run multiple aggregates. We'll return a distinct family count, and a distinct genus count, and then overall count of plants, and then the min and max assessment years, and see how that shapes out. And so again, a very compact, a single statement, very readable in its scope. Again, the analogous way of doing this in R will be multiple steps. We first probably had to select our columns and then run our aggregate. We'll use the formula style, and then we still have to clean it up with the new names. And again, it'll be a very dense call, where in SQL it's more compact. Then you can swap out groups very easily. This time we'll use our assessment indicators, the interpretive conservation status, 5 distinct values, and seeing those same exact aggregations, how they result overall. And then we can do multiple groups, group and conservation status, and see how those come out overall. I'm still running the same aggregations. And so again, you can extend You can add filters, aware clauses, having clauses to filter out the aggregates, and so you can do again a lot of very sophisticated setup in a very compact statement. So so after you source your data, use SQL also just for this initial diagnostic step. Certainly when you before you do any extensive R work. Reshaping data. This is an extension really of the aggregation. We're still using an aggregate query, but this time we're going to pivot our data by using conditional logic. Here now we're going to essentially count all the true and falses, true being equal to 1, false equal to 0. So it's essentially a count. Count all the plants in assessment year 2015, 2016, all the way down to 2020, and generate derived columns for that by our plant group. This time we're going to condition it by all the thread statuses. So overall, our same groups and seeing how thread status counts show up in all those years 2015 through 2020. So again, this is a great setup for reporting and presentation. You can certainly just add assessment year as a grouping column, but it'll be a long format and of those count of plants in those corresponding categories. But here's a nice wide format for easy readability. And then just switch out the conditional logic for other reporting. This specifically now is looking at threatened and not threatened. And then even include your original, a simpler non-conditional aggregation, and just to see how those compare across categories and number results. So again, the aggregation is a very handy tool to use in SQL that can lend itself in the data analytics. And then we can go to more advanced SQL processing. And enter here is the common table expression and window functions. CTE was introduced in the SQL ANSI 1999, window functions into ANSI 2003. And from this, you can do a lot of running calculations, lead lag variable calculations and manipulations, and then setting up moving averages or year over year analysis. Will be a very use cases for the CTE and window functions. CTE essentially is just setting up an intermediate object, specifying with the with clause. So we're actually running this aggregate query from earlier, the group and the interpretive conservation status, and we're going to use that as an intermediate object, and then use that in our final select statement. So while there's two selects, this is really one statement. It's just defining a intermediate object to be used in the final, and then in the final we'll be running our window functions. The syntax for that, you specify an aggregate function followed by an over clause, and within the over clause you can either do partition or the bottom or nothing. If you leave that blank, you're running across all rows, but by using partition, you subset by groups, and in order you're assessing across rows. So we're actually setting up a row number. We're going to do a descending count of plants across those categories, specifically interpretive conservation status within the major group. So as you can see, not threatened is the first overall for angiosperms, followed by threatened, and so on. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Recess for each column. You see that row order. Group sum, run the sum over by our same groups. So overall sum of count of plants within those groups. So obviously they repeat for every member in that group. Then we can even do a percentage calculation. Now that we have those two columns, we can take the numerator divided by the denominator, count divided by overall sum of plants in that group to get a percentage count, calculation overall. And then a running sum. Running sum is exactly the same as the inline aggregate sum, but this time you'll introduce an order by clause. Again, this is all very sophisticated calculations, but all run in one step. You can imagine doing this in R. You can use the Aave for those inline aggregates, but it further is, becomes more complex with a lot of the ordering by descending rank variables. And so SQL can really streamline a lot of that processing. And then finally, one great advantage, and it stems off of the use of the join, is join doesn't just necessarily have to be on discrete values. You can really run interval, lateral, or range joins. This can be very useful in log files, event time studies, tracking data, where you can't really match those two sets together except across an interval or overlapping time frames. And so we'll still use the CTE for this specific example. Again, the same aggregation call of the threading list. This time, so all our distinct counts and our min max of assessment year. And what we're gonna do here is we're gonna do a report where we look at 1 year and then the next year. Exactly 1 year after, and then run a series of calculations from that. And so we do just that. But one thing to note is, not only do I have a matching join off of discrete columns, I also now have I introduced a second logical call, which is essentially a subset of now condition the second result, second set 1 year after the first. And so as you can really see in R, we have to first merge and then run a subset call. SQL allows you to do that really in the same join operation, so it could really be very efficient, especially if you're working with large data sets. And then again, you can set indexes on these join columns to enhance the performance. And so this can really be very handy in that respect. And so as you can see within our major group, we have our year 1, year 2, our count of year 1, of count of plants, of threatened plants specifically, and then the year percentage change across those categories. So again, very very handy for those types of interval overlapping joint sets. So hopefully I was able to really give you a broad stroke of advantages that SQL can really land in data analytics. Again, it maintains a very readable, expressive style, following sentence semantics. So in very compact statements, it can do a lot in a very simplified format. And efficiency, and just looking at sets and in logical orders rather than iterative row value column indexing that could really increase processing time. And then so overall, really use SQL as a complementary tool in your pipeline, especially in the sourcing, if data derives from backends, and then integrate SQL in a lot of your processing. You really will find very great uses for that setup. So overall, thank you again for tuning in, and I hope this was helpful.